common mistake that people make is phase versus polarity. Phase is different than polarity. Phase, we talked about, is the starting time of one wave with relation to another, where polarity is an electrical quality of plus and minus, right? So electrical voltage plus, electrical voltage minus. People get confused a lot. So phase is different than polarity. Does anybody remember logarithms, maybe? No? Yeah. A little bit from, like, algebra. I don't expect anybody to remember math or know any physics or any of that stuff, so don't worry about that. The whole point is I'm trying to illustrate some important things. Logarithms are like the Richter scale. A 3.0 on the Richter scale versus a 4.0. You know how much more it shook at a 4.0 than a 3.0. It's because it's a logarithmic scale. So when you talk about a 3.0, 4.0, 5.0, 8.0, it goes up a lot, right? Sound is the same way, surprisingly enough, because sound actually travels around us. It's not just in one path going to your ear directly. It's not linear. It's actually based upon the fact that when I speak, the sound is coming out of my mouth and going in a spherical way out towards everybody, not just linearly to each person. So naturally, when I speak, the person that's closer to me is closer in the sphere of energy that I'm creating, and they get more energy than if it's way back in the back of the room where the sphere is huge and all this energy is going all the way around. So we actually hear in a logarithmic kind of way. And if you look at your faders on your workstation, in your computer, if you're working in Logic or Pro Tools or Ableton or whatever, they are all numbered in a logarithmic way. When we experience, and I'm just pulling this out of my memory banks, when we experience a sound getting twice as loud, it means it's going up 10 decibels. Decibels are logarithmic units. Here's an example of linear versus logarithmic. 1 linear, 1 logarithmic. 2 linear, 2 logarithmic. 3 linear, 4 logarithmic. 4 linear, 8 logarithmic. 5 linear, 16 logarithmic. So you see, it's more like this kind of a curve versus a straight curve. This is why it's important, because we hear in that way, and pitch and decibels are logarithmic scales because of how we actually experience sound in a 3-dimension rather than in a 2-dimension. Here's an example, pitch. Every octave in pitch is doubling the frequency. So middle A is 440, an octave below is 220, an octave above is 880. The Hz represents hertz, which is a unit of frequency. Or cycles per second is also a way of expressing, you know how cycles per second is a unit of frequency. So let's talk about the decibel for a second. We'll talk about that a lot, and it's used a lot in recording. 1 decibel is equal to 1/10 of a bell. A bell was named after Alexander Graham Bell. So that's the unit of sound. Using decibels, we can describe these huge differences in sound levels much easier with smaller numbers, right? That's why we use decibels. So if 0 decibels is the quietest you can hear, 150 decibels, your ears will be destroyed. So that's the range of hearing that humans can hear. And you saw the difference, right? It's a 1 quadrillionth difference from the quietest sound to the loudest sound we can hear. It's totally amazing. Your ears are totally amazing. Needless to say, if you're going to mix a record, you have to know what you're hearing, right, with your ears. And this is a really important concept to understand, that your hearing is so truly amazing. Even people with bad hearing have amazing hearing. I mean, compared to normal parameters of, say, mechanical devices or microphones or speakers. The sound pressure level disparity between the quietest sound a speaker can make and the loudest one it can make, 90 decibels maybe. We can hear much, much more than that. So microphones too, same way. So microphones, speakers, all these things that we work with in recording are basically trying to recreate what our hearing can do, right? And what our biological systems can do so much better. but basically that's how it came about in the first place. They studied how we hear, how we speak, and how we create sound, and these transducers were created mechanically to recreate what our body does. So these are sort of interesting little numbers here. This is really interesting. This is like sound pressure level of breathing is 10 decibels, all the way up to, what is this one here? I can't read it. Anyway, this gives you sort of a chart. The left are hearing damage. So you can be exposed to loud sounds for a short period of time and not damage your hearing because you are biological. But if it goes over a certain period of time, then you actually damage your hearing. So common references here. I put a few of these in here just for reference for you guys. Here, the doubling of power is 3 decibels. Doubling of voltage is 6 decibels. Humans' perception of loudness doubling is 10 decibels. So if you want something twice as loud in your mix, you raise it 10 decibels. The first couple classes are a little more like this, and then we get more into more practical stuff. Like, where do I put this microphone? How does this work? What do I do next? And that. What is an EQ? What is a compressor? All that stuff. But understanding this basic stuff, you'd be really surprised how many really, really well-known engineers and producers have no clue about this, and how important it is.